All right, good afternoon, everybody. My name is Kate McCabe. I am a master's student from the University of Minnesota, Duluth. And today I'm going to be talking about the utilization of Northeastern Minnesota wastewater treatment sludge for the use in heavyweight concrete and radiation shielding. This project was advised by Dr. Mary Christensen and Dr. Brian Hinderlater, both from the University of Minnesota, Duluth. Minnesota has some of the largest wild rice growing fields in the world, and the Ojibwe people of Minnesota have a harvesting technique they do each year and pass down to generations as a way to connect to the ecosystem around them. So due to this, the grain of wild rice is very significant both culturally and historically to this region in Minnesota. Back in 2016, John Pastor conducted a study on the health of wild rice and the effects of sulfates in the water that it's growing in, and found that this is what healthy wild rice roots look like. And this is what wild rice roots look like when they're trying to grow in sulfate-rich environments. And so it gets covered in this black gunk and essentially suffocates the root, not allowing it to grow. The study also showed that it was indicative of other issues in the ecosystem. And so if your wild rice is having issues growing, other things could be having issues as well. Back in 1973, Minnesota created the sulfate water quality standard to try and fix this issue. And so they limited the sulfate concentrations in wild rice waters to as low as 10 parts per million. For reference, for drinking water, it's 250 parts per million. So this is a very low standard. But this wasn't enforced until 2010. So there was a lot of unregulated years that this was going on. And one big area in Minnesota that produces a lot of sulfates is the mining industry, specifically iron mining. The production of the ore and the cleaning process dumps a lot of wastewater into ecosystems that has large levels of sulfates. Then overlapping a map here of where wild rice is grown in Minnesota, the darker blue color indicates where more wild rice is being grown. And so there's a nice overlap of where these iron ranges in this northern region are emitting lots of sulfates in their wastewater, upwards of 2,000 parts per million, into waters that are trying to grow wild rice. And so there's a close-up there. And so that's where the problem starts, is this wild rice is dying because there's large sulfate levels. Now, the Natural Resources Research Institute has created this method called the sulfate reduction through chemical precipitation process to remove sulfates from the water. So they take sulfate-rich wastewater, they put in chemicals to promote a precipitation process, and you're left with the clean water on the top, which is on the right side of the image there, and then this sludge at the bottom. And so my goal in the project is to keep this water treatment sludge out of landfills and find a productive use for it. And we know a lot about this sludge that's at the bottom of the tank. It's mainly comprised of barium sulfate, which can be formed through this precipitation process. It also has a common name known as barite, so you can mine it. And it is a white crystalline solid. It's insoluble in water. And the big thing that we like about it is that it has a high molecular weight. So that means that it could be used as an aggregate in heavyweight concrete because of its weight. So it usually has a specific gravity between 4 and 4.4. And so for reference, the lab sand that we'll be using has a specific gravity of 2.6, so it's a lot heavier. And so the ACI 304.3R, the heavyweight concrete measuring, mixing, transporting, and placing, talks all about heavyweight concrete and how to use it. And it's mainly dependent on the aggregates that you're putting into your concrete. And so I was looking at this barite sand mixture because that's what the material is mostly comprised of. And it has a density between 185 pounds per cubic foot and 205 pounds per cubic foot. And then compressive strengths between 5,000 and 6,000 psi. And some common applications for this heavyweight concrete that are mentioned in this guide are counterweights in construction, sound attenuation like on the sides of highways, and radiation shielding, which is what we're looking at. So it'd be like surrounding an x-ray room in a hospital or like in a dentist's office. So for the fine aggregate preparation in this study, there's the pure lab-grade barium sulfate that we use. The lab precipitated barium sulfate is this precipitation process that I talked about earlier, but just on drinking water and man-made sulfate water. So there's no wastewater. And then there's domestic wastewater and industrial wastewater, the sludges that are produced from this. And so domestic wastewater is your residential areas. Industrial is going to be your industries and factories. And so the main difference in these two waters is the organic contents in them. And so industrial is going to have a higher organic content, which will produce a darker color. So these are the sludges that we're working with. Organics means a lot of different things. So if you have like a paper mill in your town, the production of that paper, like the fibers coming off of it, would produce more organic material in your water and then giving it a darker color. So moving into the testing, first a material characterization was done on all of the different pilot samples that we were given to know what we're putting into the mortar mixtures. And so we did specific gravity testing, a total solids and moisture content test. Because these were given to us as muds, they had a lot of water in them, so we needed to know how much material was actually that we could use. Actually making the precipitated barium sulfate and knowing the combination of things in there, a particle size analysis on all the powders, and then we moved into the spread and compressive strength testing, and then from there we went into this radiation attenuation testing. So as for the specimens, it was an aggregate replacement by mass. And so for the controls, we have a 0% barium sulfate added, so it's just a sand and cement mortar that we're doing. And then from there, we replaced the sand with barium sulfate up to 50%. Once it was at that 50% mark, it did get pretty sticky because we kept the water content the same in all the mixtures. And so right now, we're not looking at adding more than 50% of this into it. And then we expanded the study to include these lab precipitated sludge, the domestic wastewater sludge, and the industrial wastewater sludge. And right now we're at just a 10% replacement, which is kind of low. But we are very limited on materials because it was pilot testing done on the wastewaters. And so we started with this 10% to make sure that everything was working and looking good. And then we do have plans to expand it out to 25 and 50% in the future. So as for the testing that's been done so far on the mortars, these are all the same mixes that we looked at before. So we looked at compressive strengths for 7, 28, 90 days, and then the densities, and then attenuation coefficients of these 3 source materials, and then different sample sizes for all of those. And so this is the point that we're at in the project right now. And so we've looked at the 7 and 28-day testing, the densities, and then attenuation testing on 2-inch samples. And so we have plans to do the 1/2 and 1-inch samples. And then the grayed out section, we don't have plans to test those. So looking first at the compression testing results, the compression testing was just a check to make sure that it could actually meet strength, and that when we're when we're replacing the sand, it would still be able to meet this 5,000 PSI mark, this goal that we had. So we wanted to make sure that replacing the sand wouldn't affect the strength, so the strength wouldn't be going down. We want it to be staying relatively the same, which we can see. The control is the 0% on the very left, so that's the black bar, and then it goes up to a 50% replacement as the colors increase. And so we can see that they all were able to meet this 5,000 PSI mark. When we look at the 10% replacements, the domestic wastewater, the pure, and the control were all able to meet this mark at 28 days. The lab sludge had a little bit of weird issues going on with it, but so that one will need to be retested just to make sure that that's all making sense. But the industrial wastewater wasn't meeting that 5,000 PSI mark, which was expected going into it. And so the industrial has a lot more going on with it because there's a lot working against it in terms of organic contents versus the other mixes. And so it wasn't able to meet the 5,000 PSI mark, but this was just to see where the strength was at before we started attenuation testing. And so then we moved on to attenuation. So that is the reduction of a force, effect, or value of something. And so in the case of this project, it's the reduction of radiation through a material. And so the test for this, you have your radiation source at the bottom of the holder. Then you have the material that you're testing. So in our case, we tested 2-inch mortar cubes. And then that counter at the top measures how much radiation goes through the material. So it's able to detect the source through the material and count how many times it can detect it over a period of time. Now, this graph here is ordinary concrete, so it has a density of 2.3 grams per centimeter cubed, so a regular concrete, and the energy and then is on the x-axis, and then the y is your linear attenuation coefficient. So this is the type of graph that we are hoping to produce from this study with the different replacement rates that we have. And so this shows how the linear attenuation coefficient changes at the different energy levels. And so this is what ordinary concrete looks like. In the terms of our study, these are the 3 sources that we're using. And so we're using a barium-133 source at around at 356 keV, a cesium-137 at 662 keV, and cobalt-60 at two different energy levels of 1.17 and 1.33 MeV. And so we're sticking in this middle range of the graph because that's within the scope of the project. If we were to go outside of that range, it gets really complicated. And so just for the sake of this project, we're staying here. And then the barium-133, the first one on the graph, that is able to produce gamma rays, which is kind of the main focus of the project. So from the testing setup, these are the graphs that we would produce. And so this is how many counts it detects at that energy source. And so your energy is on the bottom, and then the peak is always going to be at that 662 mark for our cesium-137 sample, and that's how many times it was able to detect that energy level in the material. And so once we had this graph, we were able to curve fit and find the area underneath that curve. And to find the linear attenuation coefficient from that, you take this area underneath the curve and you compare it to the area underneath the curve of a blank sample. So you're running the test without any material in between the counter and the source. And so you compare those two values and you're able to get the linear attenuation coefficient. And in this case, we are looking to see an increase in the results. And so right now, it's some of the data is showing that there is an increase in the linear attenuation coefficient. The main factor is that it's more than the control. So the control is that black bar on the left, and then this is the 10% pure and a 25% replacement. They're all higher than that control value, which is what we were expecting and what we wanted to see. One thing to note about the graph, the scale on the left seems very small numbers. That number goes into the exponent of a function, and so they're a little bit bigger of a difference than what it seems at a first glance. And so right now, the higher the replacement, it is showing an increase in linear attenuation coefficient for the pure samples. And then for the 10% replacements, it's doing the best at this 356 keV, the barium-133 source. And so we're able to, I guess the whole summary of what we're looking at is the wastewaters are showing improvement in the linear attenuation coefficient as we're adding, just even at a 10% replacement, they're able to increase over the control, especially at the barium-133 source at that energy level. In terms of future testing, 10% isn't a very large replacement rate. We understand that, and so we want to expand it out to include 25% and up to 50% to make more of an impact in using this wastewater sludge. And so that's the rest of the testing that will come is expanding out the linear attenuation coefficient testing. And then in terms of my master's project, this is actually only half of what I'm doing. So the material is also known for being a weighting material in drilling fluid. So that's why the drilling fluid images are up on the screen there. So there's also that half of the testing to wrap everything up. But thank you all. So thank you to the Natural Resources Research Institute, the Minnesota Pollution Control Agency, and the University of Minnesota Duluth. And obviously all of you guys for listening to me today. So thank you.